Dots, a simple visual method for preserving digital information. I'm Rob Hummel, president of Group 47. I'm going to introduce you to the DOTS visual method of preserving digital files. But more importantly, I'm going to introduce you to a patented method we have come up with for preserving digital images, videos, and sound files that is completely immune from operating system or file format dependencies of any kind. Literally, a way to ensure you can read a file hundreds of years into the future. We call it Bitplane image archiving, and we feel it's a future-proof method for preserving digital information. DOT stands for Digital Optical Technology System. It's the only digital storage media that stores data visually and can be easily retrieved using only a light and a lens. The DOTS design principles: archival for no less than 500 years. Data can be seen and recorded in human-readable form. Data is retrieved without sophisticated technology. It's immune to magnetism and can withstand environmental stress. DOTS can be stored anywhere from -6 to 66 degrees centigrade. It's the same form factor as existing LTO data tape systems. Hardware devices are backwardly compatible for all previous generations. But most importantly, DOTS is green technology. DOTS eliminates media and energy waste from forced migration, costly power requirements, and rigid environmental control demands. DOTS is a phase-change media composed of a patented metallic alloy sputtered on an archival polyester base, such as aramid, mylar, and estar. Standard manufacturing techniques are used to create the DOTS tape. DOTS media and prototype recorder readers were successfully built by early 2001. Group 47's new design was proven in a contract with the CIA. Group 47 has dramatically improved and simplified the hardware design with an engineering upgrade, refresh, and strengthening of the patent portfolio. Components for DOTS recorder readers employ off-the-shelf imaging and laser technologies. In 2001, Kodak Research Labs wrote 1-micron spots to DOTS using 16 individual lasers. Group 47, we've written spots simultaneously with a single laser and a spatial light modulator, all 1-micron spot size, and the 15-year-old media performed as originally specified and predicted. In 2015, Group 47 successfully completed a contract awarded by the CIA to build a laboratory prototype proving the DOTS technology. The milestones of the contract require the demonstration of writing and reading applications and document data in the DOTS visual format, and successfully writing and reading the DOTS metal alloy tape in the Bitplane image preservation format. The product. Because the data is represented visually, as long as we have access to cameras, the data will always be recoverable. Bitplane image preservation format ensures image and sound file recovery for centuries. A visual representation means all hardware will be backwardly compatible to Generation 0. It's extensible to other applications that require stable, accessible, unchangeable information. The new efficient design eliminates serpentine recording techniques and ensures record speeds in excess of 1 gigabyte per second. Each unit of DOTS media will have factory-written, human-readable instructions for building a reader on the first few meters of every cartridge. We like to call this the Rosetta Leader. Because it's visual, hardware devices are backwardly compatible for all previous generations. It has been proven that if you can store a digital copy of an image, a video, a document, or even an application on a hard drive or flash memory, you'll be able to store those same items with DOTS. What this video describes is a method of using DOTS for archiving images and sound that we like to call future-proof. The reality is, if you talk to archivists at the Library of Congress in the United States, the National Archives, or archives around the world, they'll tell you the only successful methods to archive information over history have always been visual. Whether it's a photograph, parchment, hieroglyphics, an illuminated manuscript, a film negative or print, cuneiform tablets, a book, The only successful methods have always been visual. The best practice for archiving color motion pictures and ensure they are archived properly involves what are called black and white or RGB color separations. The original color image is recorded onto 3 separate strips of film that contain a grayscale record of either the red, green, or blue color information. Since black and white film does not fade, and with the proper storage conditions, these RGB separations will preserve the color image for more than a century. That brings us to how, using DOT's metal alloy tape, we have come up with the digital equivalent of RGB separations. Now, the focus of what we're about to discuss here is motion picture archiving, but this method of archiving applies to any image medium: photographs, maps, documents, drawings, even an Excel spreadsheet, if all you're trying to preserve is the information and not the ability to manipulate the spreadsheet. Yet, with digital files, there's always been a problem. Even if you could have a file in perfect condition 100 years from now, will your operating system still support it? Some people call this one of the many digital dilemmas. Now, I'm going to show you how Bitplane Imaging solves the problem by storing the image as an image, not as a file format that may become orphaned or obsolete. But first, let's review how computers store digital information in bytes. A byte is made up of 8 bits, so in this example, these 8 squares represent the 8 bits of a byte. Any given bit can only have a binary value of 1 or 0. While a value of 0 is always 0, a 1 value, depending on the bit's position in a byte, determines what that 1 value represents. The bit position is numbered from right to left: 0, 1, 2, 3, 4, etc. If the bit value is 1 in any bit position, it takes on a value of that position: 1, 2, 4, 8, 16, 32, 64, and 128. This is how computers represent data on your hard drive, flash memory, or even in the RAM of your smartphone. They do it magnetically. With dots, we do it visually, which isn't exactly new. Decades ago, many computers would represent data visually, as with computer paper tape. Paper tape would represent a byte of data with 8 holes across the width of the film. If there was a hole, you had a value of 1. If you didn't, it was a 0. And those holes represented values of 1, 2, 4, looking familiar? And so on up to 128 for a total of 255. Now the numeric values in turn represent something else. For example, every letter has its numeric equivalent. In this example, with the word archive, the capital A has a value of 65. This is called the ASCII code value for the letter. And here we have the number 65 as it would be represented as a byte of data. That also equals 65. Then the letter R has a value of 82. And so on. Now I've taken that word archive and saved it into a text file, so that the binary values of each letter are stored in that text file, and in turn, I have saved that file to dots, where those binary values are represented visually, just like on the paper tape. In this magnification of the dots image of the data, we see the blocks that represent the start of the file marker, and then the dots that represent the data visually. Each one of these dots is a binary 1. Let me zoom in closer to explain. We are now looking at the very beginning of this text file of the word archive. Since the letter A is represented by a value of 65, we see here it represented with the binary value of 01, 00, 00, 01. The letter R is represented with 82, or 01, 01, 00, 10. If there's a dot, it has a value of 1. If there isn't a dot, it has a value of 0. The same goes for the letter C with 01, 00, 00, 11. So, you see the basics of how dots represents the data visually of a text file. Now we'll take this digital image of a shrine in Tokyo, and this is what the JPEG file of that image looks like when recorded to dots. Quite a bit of data, and not so easy to figure out without the right JPEG software. However, as we stated at the beginning of this video, the challenge of any file, even if kept intact and in perfect condition for decades, will the computer operating system be able to read the file in the future? Here's the future-proof solution we have developed with dots that is not so unlike black and white RGB protection masters. Let me explain. Here we have a 35mm film JPEG image that is a resolution of 4K across its width, what is called Super 35 or Super 1A5 in motion picture parlance. This could just as easily be an image captured digitally as well. As mentioned earlier, the proven method to archive motion pictures is to segment out the color image into its grayscale values of red, green, and blue, and print or record these out to 35mm black and white film. In order to be more clear in how our digital equivalent works, I'll zoom into this segment of the Strategic Air Command banner, and then I'll zoom in again, so that we're now looking at a 12 by 12 pixel area of this 4K image. Basically, we're looking at a part of the R of the word strategic. Now we'll take that 12 by 12 area and illustrate that a digital image can also be represented with red, green, and blue grayscale components. In the same way that there are numbers to represent letters as we showed earlier, each value of red, green, and blue in this digital image has a value from 0 to 255. Now we'll continue our zooming in here to these 4 pixels in the image, and then zoom in again to this single pixel with values of red 182, green 125, and blue 82. If we were to represent the 182 of red in binary, we would have 0, 1, 1, 0, 1, 1, 0, 1. With dots, I can represent those values visually with a dot for each value of 1, and where shiny, or black under polarized light, has a value of 0. So from right to left, shiny, white, white, shiny, white, white, shiny, white is easily translated back to 0, 1, 1, 0, 1, 1, 0, 1. And if we add up the values for each of those bit positions, we get 128 plus 32 plus 16 plus 4 plus 2 equals 182. The same applies for the value of 125 for green in this pixel, with adding up the binary values of the 1 bits equals 125. And again with the value of 82 for blue, adding 64 plus 16 plus 2 gives us 82. Recapping here, what you should understand is that we have represented bit values of each bit, not literally with a number 1 or a 0. We have shown how those values can represent a 1 or a 0 depending on whether the dot's media is light or dark. Now let's take this a step further, and instead of representing the value on 1 pixel, how do we do it for the entire image? Here, we've zoomed back out to the original 12 by 12 pixel area of the image we started with. The left represents the grayscale of red for this 12 by 12 area. The right is showing the binary value 1 or 0 for the first bit position of this 12 by 12 area. If I can represent that first bit position with 1s and 0s, I can also represent them on DOTS metal alloy tape with light and dark. Using a camera and employing computer image processing, I can quickly calculate the values of the first bit position for each of these pixels, simpler than reading a barcode at the grocery store. In fact, even a human can easily see that each of the light squares in this image has a value of 1. Now, if I can do that for the first bit position, that means I can do it for the second bit position too. Then the third bit position, fourth bit position, all the way to the last bit position. I can create 8 image maps that, when combined, will create the full color image of this 12 by 12 segment of the picture. This, of course, applies to the bit values for the color green and for the color blue as well. As you can see here, with 24 image maps, I can recreate the original JPEG file, in this case, without any fear of an operating system or file format no longer being supported. This technique can be applied to any image format, TIFF, PNG, DPX, etc. Now, if we zoom further out, here we can see with 8 images, we can calculate the bit values for every red pixel in the image. And with 24 images, we can recreate the entire original image without compromise. Here's an example of how the 3 red, green, and blue bitplane images would be recorded to DOTS metal alloy tape. We also have a solution for sound files as well. Now, how do we put it all back together again? Well, we start with the 8 images that represent the red pixels, and then the bitplane images inform the saturation of red for each pixel based on the values for each bit position. Those 8 images are then stacked up like a layer cake with position 1, 2, 3, 4, and you can begin to see the image form with all the cumulative red values in the image, giving you the perfect representation of red in the image. The same applies for the bitplanes representing the colors green and blue in the picture. As the layers accumulate their respective values, the image begins to reform. And then it's a simple matter of combining the red, plus the green, plus the blue to recreate the original color image. Quite simply, resembling the same technique used with black and white film separations we mentioned at the start. We're almost done here, but we need to tell you about one more benefit to DOTS bitplane image archiving. There's a problem in the world of image archiving where a digital image can become damaged by a random bit flip, where the value of a bit changes from 0 to 1 or 1 to 0. This is caused by file corruption from magnetism, age, or cyber attack. Here we took a 24-frame motion picture sequence of this aircraft image. Using an algorithm, we randomly flipped 13 bits across the 24 frames. Not 13 bits in each frame, but only 13 out of all 24 frames. Of those 24 frames, not surprisingly, 14 of the frames were untouched and did not have a problem. However, 6 of the frames, we are no longer able to open them after experiencing the bit flips. And here's what the remaining 4 look like. If you look carefully, you can see some distortion of the image around the nose of the aircraft. However, these frames should be a little easier to see the problem. These are the results of just flipping 1 or 2 bits in these images. Now, let's show you what happens when you flip a bit in an image stored with DOTS bitplane image archiving. In fact, here we have randomly flipped over 45,000 bits in this single image with little impact. Not 1, not 13, but 45,000. Here we've taken it a bit further. Flipping 1% of the bits in the image are over 380,000 flipped bits. Why is bitplane image archiving so robust? Well, with this technique, a flipped bit only impacts the value of that bit, basically, just changing the color of that pixel. Or, if we flip the third bit position in this illustration, it would just change the value of 182 to 178. It's hard to see any effect in the picture because the impact is so minimal. If we zoom in here on the aircraft photo, you can see the colored confetti of the flipped bits. A much easier problem to deal with versus when 1 bit can cause this much damage to an image. To further illustrate, we can save an image in its native format, or we can save it with bitplane imaging. Which do you think will be easier to figure out in 100 years? This technique is so novel and unique that in November of 2016, Group 47 was granted a patent on bitplane imaging. And the patent applies to storing data with this technique on any media. In summary, reading DOTS data with a camera ensures forever readability. It eliminates concern over file format dependencies in the future. There are no more orphaned image or sound formats. It eliminates migration due to fear of media failure. It eliminates migration to maintain file format compatibility. And it guarantees digital image and motion picture archive stability for centuries.